we will consider two solved examples, one with inequality constraints and the other one with equality constraints. As a reminder, this is the general form of a constraint optimization problem. This is the Lagrangian. These are the first order conditions: the primal feasibility, dual feasibility, complementary slackness, and stationary conditions. And this is the second order condition. Now, in these examples, we don't really consider the second order conditions because of the simplicity of the problems. And we don't really care for the primal feasibility because they are, in fact, part of the constraints, the inequality and equality constraints. And the dual feasibility condition is also easy to remember because lambda has to be greater than 0, lambda corresponding to the inequality constraint. So we really need to care for the complementary slackness and stationary conditions here. Example 1, inequality constraint. The objective is to maximize with respect to x and y, f of xy equals x squared y. Subject to the constraints, x plus y is less than equal to 9 and 2x plus y is less than equal to 12. The Lagrangian is x squared plus y minus alpha is a Lagrange multiplier, x plus y minus 9, because this constraint translates to x plus y minus 9 is less than equal to 0. And this constraint likewise translates to twice x plus y minus 12 is less than equal to 0, giving rise to this term in the Lagrangian. And I have used negative here with the Lagrange multipliers alpha and beta because it is a maximization problem. And alpha and beta, both being associated with inequality constraints, must be greater than equal to 0. Now, this is the general problem-solving strategy for cases with inequality constraints. We must consider all possible cases of active and inactive inequality constraints. Each inequality constraint can be either active or inactive. So there are two cases per inequality constraint. And since there are m equals 2 inequality constraints in our case, this is 1 and this is 2, we will consider 2 to the m equals 4 cases. So there will be 4 cases to consider in our example. In each case, in each of the 4 cases, active inequality constraints are equality constraints. And for each case, this is what we do. Using all equality constraints and stationary conditions, solve for primal variables. Check feasibility conditions, discard case if infeasible, and retain case if feasible. One caveat here, when checking the feasibility conditions, in general, we must also check the dual feasibility conditions to see that the Lagrange multipliers corresponding to the inequality constraints are not negative. If they are negative, then we discard the case. But in our simple case, we don't need to check these, only checking the primal feasibility conditions is good enough. And then for all cases that we retain, we compare value of the objective function, and then we retain the best case as the output of our problem. Now back to our problem. The complementary slackness conditions are alpha times x plus y minus 9 equals 0, beta times twice x plus y minus 12 equals 0, and to get these stationary conditions, we differentiate the Lagrangian with respect to each primal variable, which in our case is either x or y. So derivative of the Lagrangian with respect to x is, derivative of the first term is twice xy. Derivative of the second term with respect to x is simply minus alpha, and likewise derivative with respect to x of the third term is minus twice beta. So that should be equal to 0. That gives the first stationary condition. The second stationary condition is when we differentiate the Lagrangian with respect to the second primal variable y. And so let's take the derivative. The derivative of x squared y with respect to y is x squared. The derivative with respect to y of the second term is negative alpha, and the derivative with respect to y of the third term is negative beta. So that's equal to 0. So these are the two stationary conditions, and these we need to retain. Twice xy equals alpha plus twice beta, and x squared equals alpha plus beta. We won't need the complementary slackness conditions in this little example. Now there will be 4 cases since we have two inequality constraints. Now one of the cases will be alpha equals 0 and beta equals 0 when both cases are both these constraints are inactive. Now, in that case, if we look at these two expressions, when alpha and beta are both zeros, twice xy is 0 and x squared equals 0, which means that x equals 0. And since x equals 0, this cannot be the maximum. So we don't really need to consider this case. Alpha equals 0 and beta equals 0. Y can be anything here, by the way. It doesn't have to be 0. Only x has to be 0 for this. So we don't consider this situation where alpha and beta are both zeros. That is, when both the constraints are inactive. Case 1, alpha equals 0 and beta is greater than 0. Which means that this is the Lagrange multiplier corresponding to the constraint x plus y less than equal to 9. And when we say that alpha equals 0, it means that this constraint is inactive. In other words, x plus y is strictly less than 9. Now, beta greater than 0 implies that the second constraint is active, which means that twice x plus y is actually equal to 12. So what we get is, since alpha equals 0, replacing alpha with 0 in this expression, we get twice xy equals twice beta, or xy equals beta. Replacing alpha with 0 in the second expression here, we get x squared equals beta. And since we noted that twice x plus y is equal to 12, which is the active constraint, we have this expression. So we have these 3 equations and their equalities, and we need to solve for x and y. And the solution is x equals y equals 4. The function x squared y is 64 in this case. And you can check the feasibility conditions. X plus y is equal to 8, which is less than 9. So this is in fact an inactive constraint, and it's feasible for x and y equals 4, and so we retain this solution. Next, we consider case 2, where alpha is greater than 0 and beta equals 0. Since alpha is greater than 0, this is an active constraint, which means that x plus y equals 9, and beta is equal to 0 implies that twice x plus y is strictly less than 12. And letting beta equals 0 in this expression, we get twice xy equals alpha, and letting beta equals 0 in this expression, we get x squared equals alpha. Solving, we get x plus y, from the active constraint, we get x plus y equals 9. Solving, we get x equals 6 and y equals 3. Now we need to check if this is feasible. Twice x plus y in our case becomes 15, and that violates this constraint. Twice x plus y should be less than or equal to 12. So this case is infeasible. We discard it. Case 3 is when both alpha and beta are greater than 0, which means that both the constraints are active. X plus y is equal to 9 and twice x plus y is equal to 12. So we get both these expressions, which correspond to the active constraints. And the solution is x equals 3, y equals 6. And it can be seen that this is feasible because we just solved for these two expressions being equalities. And f of xy is 54 in this case. Since this is a feasible solution, we retain it. So now we have two cases that we retained, case 1 and case 3, and we compare the value of the objective function that we need to maximize. Since f of xy is higher in case 1, which is 64, than in case 3, which is 54, we retain case 1, and that's our final solution. X equals y equals 4. Example 2 is a constraint optimization problem with a single equality constraint. This figure is relevant. Consider the shape, the brown shape. There are two parameters. One is the breadth b of the shape, and the other parameter is h, the height of this square portion. This upper portion is a half circle. The area of this whole shape is a bh plus pi over 8b square, and the perimeter is b plus twice h plus pi over 2b. And our problem is maximize with respect to bh the perimeter, which is b plus twice h plus pi over 2b, subject to area is constant a. bh plus pi over 8b square is equal to a. The area is fixed. Now, the general problem-solving strategy with equality constraints is there are no dual feasibility or complementary slackness conditions, so we don't even have to worry about them. And we solve for the primal variables using the stationary condition and equality constraints. Returning to the COP with a single equality constraint, what about B and H, the two parameters of the problem, being greater than or equal to 0? Now we observe that the constraint optimization problem does not admit any negatives, we only have positives in the perimeter and we have positives in the area. And so it's just common sense that the solution will eventually yield B and H is greater than 0. So we will ignore these constraints, B greater than 0 and H greater than 0. So we will only have a single equality constraint to pay attention to. The Lagrangian is LBH mu equals B plus twice H plus pi over 2B minus mu times the area BH plus pi over 8B squared minus A. Now I chose a negative sign just for convenience. It really doesn't matter because mu can be both positive and negative. Taking the derivative with respect to H, now that's the first stationary condition, we get twice minus mu B equals 0, whence mu B equals 2. Differentiating with respect to B of the Lagrangian, we get 1 minus pi over 2 minus mu H minus pi over 4 mu B equals 0. Now, observing that mu B equals 2, we can replace mu B with 2, whence the second and fourth term of this expression cancel out. We are left with mu H is equal to 1. So, observing that mu B equals 2 and mu H equals 1, we see that B equals twice H. Now we have the equality constraint, and replacing B equals twice H and solving, we see that 2H squared plus pi over 2H squared equals A, whence H equals square root of twice A over 4 plus pi, and B equals square root of 8A over 4 plus pi.